everyone. Thanks for coming. This is the second week of the Blackset seminar. Today we are lucky to have corner Jerzak. He is a PhD candidate at Gov department, and today corner is going to present detecting and characterizing latent influence dynamics in social science data using machine learning, and this is his job market paper. So corner.
Thank you, Sochiro. Thank you all for coming to this presentation today. So today I'll be talking about something which I think is fundamental to the social sciences, and that's influence and interaction. Influence and interaction are fundamental at really all levels of political science, from the international realm, where states are battling for hegemony, to the realm of organizational politics, where different groups collaborate, compete, form coalitions, and also to the level of individual politics, where voters argue with one another, where they attempt to convince other people of their opinions and sway them in some way. And so these interactions, I think, form a fundamental basis for political science, but they've been difficult to characterize quantitatively for reasons which I like to discuss or illustrate using an example. So the example that I'd like us to go through is this voter turnout experiment, which took place in Suffolk in the United Kingdom. And in this experiment, the treatment of interest was contact by Liberal Party canvassers, and the outcome of interest was a measure of turnout. And in this experiment, we can imagine that there's this particular voter, and that voter is person I. And person I lives in Suffolk off of Bishop's Hill Road, and this person is not independent from other people in the experiment. This person is potentially connected with other people around them in a host of ways. So,
corner, sorry to interrupt. Is the slides not moving?
Are you clicking the
slides? Yeah. Sorry, we had the same issue last week too.
Let's see. Can you see this? Are things moving? All right. Yep. So this is person I off of Bishop's Hill Road. This person in this experiment is not independent from those around them. This person is connected with others in a whole host of ways. So here we could see person I's co-working network. So some of the co-workers could have been in the experiment, and some of them may have received treatment, and some of them may have received a control intervention. But that's not the only sort of influence dynamic at play here. We could see that there are others in the experiment who are connected to I in different ways. So here we could see person I's colleagues in the Liberal Party. And here we could see person I's school friend. And all of these different influence patterns could be at play in different ways for different experiments and for different outcomes of interest. So if the outcome of interest is turnout, the way in which all of these influences aggregate together could be different than when the outcome of interest is the vote choice at the ballot box. In addition, different interventions would have different influence structures associated with them as well. If the canvassers are from the Liberal Party, that could
I can't hear you.
Corner, you're muted.
He went on mute.
Is this better?
Yes.
Okay, I'm not sure how that happened, but hopefully it doesn't happen again. So in this experiment, not only are there all of these influence dynamics present, but experimenters usually don't observe even any of them. Usually experimenters just observe who's receiving the treatment in this study. In addition, we might observe a few things about each person, but we don't observe anything directly about whether one person is connected to another. And there's here an unbelievable degree of complexity in who influences whom. People aren't only influencing unit I, but there are all sorts of influences. There are arrows going every which way, but we don't observe them in general. In addition, we have to think about the equally challenging question about how influence manifests itself in practice. Even if we knew who influenced whom, how would we translate that knowledge into knowledge of the outcome? So in this project, I've sought to address some of these questions, first by developing a new machine learning framework for inferring influence. In this framework will, I'll call it the deep latent influence network, and we'll be developing a machine learning paradigm for inferring some of these influence dynamics. In addition, we're going to establish the validity of a powerful statistical test, which is going to use that machine learning framework in order to answer questions about whether one person is influenced by others or not. And this will work in experimental data, and also in extensions will have applicability as well in the observational context. Moreover, we'll be able to answer individual level questions about influence using this framework. So questions about whether a single person is influenced by some group. And finally, we'll devise a way to summarize influence effects without directly observing who influences whom. So this is a summary of the contributions here. But before we start to move through these three things, I think we first need to ask ourselves, what do we mean by influence? So what I mean by influence here is that when something happens to person J, that somehow alters person I's actions. So we can think about a few examples. Influence is likely present in the international context, in the context of arms races. So we could imagine that if we learned that Russia increases its military spending in a year, we might expect that in that same year, the US would also be likely to increase its spending. And there are, however, some situations when influence is probably not present. So in the context of a survey experiment that's done online, we could consider whether a particular person receiving treatment 1 in that survey experiment, whether that has any influence or whether that has any gives us any information about whether person J reports strongly agree on some other question. And here, influence is probably not present. Learning about what happened to person I in this experiment probably doesn't tell us anything about what happens and what person J decides to do in that study. But there are a whole host of questions in the social sciences where we just don't know. For example, a senator might receive a campaign contribution from a group of lobbyists, and it could be that contribution would induce a colleague to vote yes, or the senator is communicating with colleagues and could be influential in some capacity, and that senator receiving this contribution could affect whether the colleague votes yes. But we don't know. It's an empirical question, and we like to develop tools for answering that empirical question using the most information we have at our disposal. So just to summarize this, to put things in a maybe more formal way, no influence can be translated into this independence relationship. So when there is no influence, then what happens to J is independent from what I ends up doing, from I's action. And when influence is present, information is carried through from one to the other. So if we know what happened to J, then that tells us something about I's action. So there's this dependency here. It's not independent, it's dependent. But we don't want to stop here. We want to answer this question about independence using all the data at our disposal. So the more information that we use to answer this question, the better answer we're going to get. So in particular, the question that we have before us is what we had before here, but whether what happens to J, whether that somehow tells us something about what I's action will be. And here we're going to try to use or condition on everything that's at our disposal. And everything at our disposal could include things such as all the covariate data that we have, and that could include an observed network of some kind. We also would want to exploit other things as well, other sorts of data about what happened to everyone but I in this independent variable W. And finally, we'd also like to use information as far as we can about what happened, what everyone but I did in this setting. So the intuition here is we're going to try to answer this question using all the information at our disposal. In this to answer this sort of question, we'll first think about how we can answer this in a rigorous way. What sort of statistical tests can we devise for answering that question that we've listed in the above? And the framework that I'll be sort of building on is the Model X conditional randomization testing literature. And before going through that, first I'll just introduce a little bit of notation, and then I'll go through what that testing framework is and how we can extend it to this case. So in this case, I'm going to proposit that there are two sets of units in this study. So one set of units, Ni, these are units whose influence on unit I we are going to test. And this, we can call this the testing set. So this group, we're interested in assessing whether this group in the set Ni is influential in some way on unit I. But there's another group whose influence on I we won't test, and we'll call this the control set. So we're breaking the observational units down into these two sets based on whether we're interested or not interested in assessing whether each group influences unit I in some capacity. So the null hypothesis in this test that we're going to work with and build on going forward is the following, and it's going to be, is what happens to everyone in the testing set, is that and the outcome for unit I, are those two things conditionally independent? In other words, does this sort of relationship hold? Do we learn something about I's action if we observe, or if we learn something about what happens to everyone in the testing group, or do we not learn anything about what I will decide to do? And we're going to condition on all that information that we just have discussed. And the theoretical work that we'll do here is we'll be extending this Model X framework here to the non-IID case. And we're going to show that for any G, for any test statistic function that's fixed, we can show that this test statistic function G, when that is applied to what really will happen to people in the testing set, when that function is applied to what really will happen, in addition to those other things, such as I's outcome, this test statistic under the null hypothesis will show has the same distribution as that same fixed test statistic applied to a simulated version of what really will happen to everyone in the setting. So in the experimental context, this simulated version is easy to work with. We're just going to be drawing things from the treatment distribution. So if we have an experiment where half of the units get the treated intervention and half the units get the control intervention, then we will resample the treatment and control assignments exactly like that to get the simulated version for the treatment vector for people in the testing set. And the distribution of this fixed test statistic function will be the same in the two cases. And the beauty of this here is that this G function, this test statistic function, can be anything so long as it's fixed. And what that means is that we can build on really the machine learning paradigm, where we're going to develop a complicated G function, which is going to maximize our ability to detect influence when it's actually happening in a way that I'll describe in the next slide. So what we'll do, theorem 1 here motivates this following conditional randomization test. So in this conditional randomization test, we'll be able to get exact p-values using theorem 1, and we'll perform the test like so. So our null hypothesis here is that what happens to people in that testing set and unit I, those two things are conditionally independent. That's the null hypothesis. And the test that we develop here is the following. Given the data that we have observed from the experiment, we're going to sample that the treatment vector for everyone in the testing set from its known distribution. And then we're going to recalculate a test statistic. And there's some recent work showing that something like the following could be a particularly powerful test statistic. So the test statistic that we'll consider here is what we see here. So the test statistic will be something like whether the predictive error in predicting the outcome for unit I using the resampled version of what happened to everyone in the testing group in the experimental setting. So we can think about this F hat. That's going to be, we're going to try to learn this using a machine learning paradigm in a way that I'll discuss in the next few slides. But we're going to try to build a model for the outcome. And that model is going to use information about what happened to people in this testing set. And we're going to compute the predictive loss, or the degree to which.
Sorry to interrupt.
Yes.
Could I just ask a clarifying question, please?
Sure.
Thank you. So you have this test statistic and you're going to be doing a simulation, and I think you said you're going to be replicating the assignment mechanism that was part of the original experiment, correct?
Correct.
And then is your but you're looking for influence, which means that you are allowing for there to be direct treatment effects. And do you have to like strip out the direct treatment effects in your simulation, or can you just give me some orientation on where you're going? Because I think I'm getting a little lost.
That's a great question. So I think there are a few ways to do it, but one way that this can be accomplished is if we go back. So we can think about this function, this f function, and we can think about the parameters associated with that function. And what we can do is we can learn something about those parameters using all of the data in the control set. So we're not going to be simulating the control, we're not going to be simulating those assignments for the control set. So what we can do is we can, one way to accomplish this would be to build a model for this thing here using the observations in the control set. And then to take that model and the parameters from that model and apply it here using the full slew of information, including the testing set. Does that address the question? So we can the function that we're going to learn here can incorporate direct effects, and we'll get information about those direct effects by using the outcome and by using the treatment data from the control set of units.
And then under the null, you don't have to worry about those direct effects being influenced because you just assume there is no influence.
So under the null, we can still have direct effects, but what we'll be testing here is those influence effects. So in practice, the set of units that will fix in terms of their treatment values, most likely unit I would be a part of that set of units whose treatment assignment we're fixing, and we're not simulating. Since in practice, we have other ways of testing for direct effects, but we're more interested in spillover effects and in influence effects. So we're gonna, in this case, we're gonna keep fixed in general the treatment assignment for unit I, and we'll be permuting or simulating the treatment assignment values for those other units in that other set. Yeah, that's a great question.
I have sort of similar, I'm getting lost here. So you pick I, or what, do you do this for every I, or?
Yeah, so that's a good question. So there are a few different ways to do it. The theoretical results can be extended to test sets of units at once using the same test statistic. We can also, but in general, I think we can do this for a single I. We can do this one I at a time. So we specify unit I, and then we specify the units which we're gonna put in the control set, and the units we're gonna put in the testing set. I think there are a lot of interesting things we can say about how to do this in a way that maximizes our ability to detect influence effects when they're present. But yes, so in the framework, so in the way that I'm presenting it here, this test statistic is going to be testing an individual level influence effect for a particular unit. And we're going to, in particular, the null hypothesis is about a specific, or is about whether a specific group of people or a specific person are influential. Although we can extend this by having sort of multiple null hypotheses and aggregating up the test statistics, or we can also form sort of aggregate test statistics and do this for testing for multiple sorts of independence relationships at once. But I think the simplest thing to think about is doing this for one unit at a time.
So how is this different from what like Peter, I see Peter here, and some other people have been doing, like this conditional randomization test, right? Could they fix the particular unit's treatment status and then randomize the rest of the units?
Mm-hmm. Yeah, so I think that's a good question. Here, so there are a few different sort of traditions that in the interference literature, there are a few different ways that that conditional randomization tests have been used. And one of the sort of leading traditions, or one of the leading methods, is to assess a sharp null hypothesis. So we could, so in the experimental context, we have the treated group and the control group, and we can look at different subgroups within the treated group, and we can find subgroups for whom under a null hypothesis of no interference, where a sharp null hypothesis is going to hold under that null hypothesis. So we can use permutation inference in that setting. So that's one of the traditions that is prominent. I think one difference here is that the test statistic that I'll use, we're going to be conditioning on all of the observed outcome data. So if we go back to theorem 1 here, all of the observed outcome data is going to be used in some way. So this G function can be honed using potentially all of the outcome data of interest. It's just that we can only apply this test statistic function in the test to these two sort of two things in this way as described in this case. So it's building from a somewhat different tradition, but I think a lot of the intuitions are the same about sort of we're not examining here a sharp null hypothesis. We're examining a null hypothesis that is associated with this conditional independence relationship.
Yes, I guess then I'm confused. I think Luke's maybe trying to get at this, but you're conditioning on the y, right? The y minus I.
Yes.
And then you're permuting the w, I guess, potential influencers treatment, right? So doesn't that w and y are related? Y minus I and w ci, or ni, sorry, w ni, I guess. Isn't that a direct effect? So you condition on your own outcome when you're permuting the treatment of your own treatment status. So unless you assume there's no direct effect, you have you don't know the distribution, right?
So are you saying we permute the direct? Can you repeat that one more time?
Like in the previous slide, you have conditioning on y minus I, which is observed data for all the units other than I, right?
Yes.
So that's conditional, like that's dependent on the w n of I, is that right?
Yeah, so wi, that's the,
go ahead, sorry.
That's a w minus I, that could be, w minus I could be sort of related to n of I. There could be sort of what happens to people in the testing set could be related to their outcome. I mean, that's certainly true. So the test statistic that we're working with here is specific to observation I, and we can show that using the resampling framework that we can actually use the data from these observations in order to test this null hypothesis of independence here. Does that address your question, or?
I guess I don't have an intuition, like, because y minus I is a function of w n of I, right? Because w n of I could affect y minus I, is that right?
It could.
So I don't quite understand what that distribution is under the null, like the conditional distribution of w's. But maybe, I don't know, maybe I'm missing something, but.
Yeah, so, and I have some slides at the end which could get into this a bit more, but the simulated version here is not being generated we're generating the simulated version not looking at the outcome data in any capacity. So that's, I think, part of the intuition here for why we can condition on these observations. What really will happen to people in this testing set, in the simulated version of that, if we formulate the test statistic like this, we can condition on that data. That's the benefit of that is that this test statistic then can be made more powerful. So in other words, the simulation here isn't taking into account information about the potential ways in which the outcome for everyone in the testing set could be related to the treatments for people in the testing set. We're generating the W's without using that information.
Maybe we should get more detail by letting you move forward, and then we'll circle back to bug you later on if we're still confused.
Okay, that sounds good. But I think this is definitely an important part of the work, and I'm happy to talk more about this theorem in the end. So having said these things, so this is the test, and we're permuting here like the treatment vector or the treatment variable for everyone in that testing group. And the model here is built using potentially all of the observations. And under the null hypothesis, we see that the above relation holds. And that's what allows us to form p-values using this test statistic, using this test statistic. So the intuition is that if we have a particular model for predicting the outcome, and if that model includes information about people in the control group, or in the control set and people in the testing set, our prediction will get worse if we use the randomized or the simulated version of what happens to everyone in that group, compared to if we used what actually did happen to everyone in that group. So that's the intuition here. We have a particular model, and we can train that model using, we can do whatever we want using the people in the testing set, what happens to them in addition to their outcome data, and we can use the covariate data at will as well. And under and the intuition is that when we permute the treatment vector for everyone in that testing group, the error gets worse when influence is occurring. So in other words, if there's information contained within the assignment of other people for predicting unit I's outcome, then we see that the predictive accuracy is worse. The test statistic is bigger than when we use the true value. The error is bigger when we use the simulated versus the true value, and the p-value therefore would be small. So this is the intuition for what will come later. But we can circle back to this and address any remaining questions once I've talked through a few more things. So that's the intuition here. But we might ask, and I think some of the questions are asking, how do we calculate, or how do we formulate this model for what happens to everyone in the control group, what happens to everyone in the testing group, and in addition to the covariate data? How can we form a model such as that? And there in the world, this outcome data exists in some way, and this outcome data is some true function of what happens to everyone in the experiment, in addition to the covariate vector for this person. There is some true model that exists out there, but there's an unbelievable amount of complexity in this model. This complexity takes on two forms. The first form of complexity, or the first question that we need to address, is who likely influences who. And the second task that we'll need to address is what is the impact of influence on the outcome. So these are the kinds of questions that we'll need to answer in computing the test statistic, which could involve something like our predictive loss in predicting the outcome using the simulated versus the true outcome data for everyone in that testing set. So moving forward to the first task, this is the task of influence discovery. So the intuition for this influence discovery can be conveyed by looking at this here. So let's return to unit I in the right panel, and let's think about unit I, and let's think about other people in the experiment. So unit I is not isolated. There are other people in the experiment, but more than that, there are other ways in which we have data about the potential interaction between these two people. So we can form some sense for whether person J influences person I by looking at things like their covariate data. So this could include things such as where is each unit located. This could include things such as which political party each person is a part of, in addition to things like whether each person voted or not. So person J has no history of person J has a history of prior voting, but person I has no history of prior voting. So the intuition that I'll build in the following model is that we can use information in the covariates and in any measured network to improve our predictions about what the probability of connection should be between any two people. So the assumption that we'll be making here, which will reduce the complexity of this problem, is that the probability of connection between one person and another in this interaction is a function of person I's type and is a function of person J's type. So this is going to be a latent stochastic block model, and we choose this kind of model in particular because it can represent a large class of interaction types. It can't only represent sort of homophily dynamics where close people are more likely to be connected, but it can represent a large a class beyond that as well. And there are beautiful theorems about universality of the stochastic block model for representing these sort of interaction dynamics. So what we'll do here is we'll build a model for the probability that any particular person takes on any particular type using the covariates. So the probability here, this line here will just say that the probability that I and J, that J influences I, that's just a function of the receiver type. So this R stands for receiver, the receiver type of unit I in this interaction. So unit I is receiving influence here, and there's a specific latent type associated with that. And in addition, we can think about the sender type for unit J. So unit J is sending influence to unit I, and there's a specific latent class associated with that sending dynamic as well. And conditional on the sending and receiving type, the probability of this influence being set to 1, the probability that J influences I is going to be drawn from Bernoulli distribution with a particular parameter. And the next step we'll take is that we'll try to learn the probability that that person I is a receiver type R in this interaction using the covariates. So to give just some intuition for this, if we have a school classroom and if we have students in that classroom, we can imagine there being 2 types of students, introverts and extroverts. And the probability that 2 extroverts are connected to each other is high, but the probability that 2 introverts are connected could be quite low. And the probability that an introvert and an extrovert are connected could be in the middle somewhere. And we'll use our covariates or any noisy measure of the network to improve our prediction about what those probabilities should be, about whether one person in that school will be an introvert or will be an extrovert, or any sort of other different latent class that we'll try to infer through this approach. In addition, we'll do the same thing for the sender types. We're going to have some complicated function of person J and person I's covariate profile or any noisy measure of the network. We'll have a flexible function relating their covariate profiles to this overall probability. We want this function to be flexible. We don't want to impose much structure on it. So we'll be using a neural network architecture for taking information about the covariates and for translating that into these probabilities. We'll use this architecture in particular since this can approximate any continuous function, and there's also some recent work about how neural networks trained using gradient descent can arrive at global optimizers. So there's some nice theoretical properties here, which we'll try to exploit in addition to the properties of the stochastic block model. So moving forward, the overall connection probability will just average over the uncertainty in the receiver and in the sender types. So this is the model that we'll use for inferring those influence probabilities. And that model will be flexible in the ways described here. So this is how we've attempted to address task 1. But we don't only have one task, we have 2 tasks. The first task is how do we infer who influences whom, but the second task is equally challenging. How do we learn about the manifestation of influence on the outcome of interest? So the outcome model here is not a trivial one. So to give you an example here, let's go back to person I. And person I in that experiment has a whole host of people around them. And let's say we knew that all these people here were influencing person I in some way. Even if we knew that, it would still be unclear how we translate that knowledge into a prediction of the outcome. So the simplifying assumption that I'll make is going to generalize something that's known as the stratified interference assumption. So I'm going to take this complexity here, and I'm going to distill it down through a simplifying assumption. And that simplifying assumption is that the outcome is determined in some way by the sum of treated connections within these latent subgroups. So we don't want the outcome just to be a function of the sum of treated connections, because in a dynamic like this, we might imagine that in a competitive setting, treated connections in one group and in another group could have opposite effects if these groups are competing with one another in some way. So instead, we'll try to loosen that to some extent by assuming that these latent classes or the sum of treated units within the subgroups is ultimately what will matter for the outcome. So this I'll call the generalized stratified influence assumption, and it can be written like so. So the outcome in this model, we're going to assume that it's some flexible function of this number of treated connections in each of these subgroups. And again, we want this model to be flexible, and that's why we'll have, again, this neural network architecture here for taking in knowledge of the number of treated connections within these subgroups and converting that into a prediction for the outcome. And there could be, in this model for the outcome, there could be other components to it to account for treatment effect heterogeneity or for covariate effects. in those sorts of things. So this is just taking in that one component of the outcome model, not the whole outcome model, but just that one component which is associated with influence.
Quick clarifying, when you say number of treated connections, those are those probability things that you talked about, like, and then flip and you get a heads with whatever probability, and that means that you have influenced, which means you get a count of 1 in terms of this function.
Exactly. So
but you, oh
sorry,
and that function right now it's written as G, and then it's the number, it's just you're fitting a neural net, but there's only K inputs to this particular neural net, which is essentially a bunch of integers of the number of the estimated number of connections for each of these latent groups.
Yes. So here we would have a total of, yes, that's right. We'd have K different components to this, and we could then apply a nonlinear function on top of that.
And just so I have a sense of where we're going again, what's K for you normally? Like, what's a ballpark K?
So K, I think it's a good question. I think we could do something like cross-validation to try to fit this K. I think choosing K to be 3, so if K is 1, then that doesn't allow for different differential dynamics between these competing groups. So there are a few choices. We could assume that the subgroups here in this model for the outcome are the same as the ones in the model for the influence probabilities. But I think allowing K to be greater than 1 could help, at least in allowing for us to account for competitive dynamics where having treated enemies and treated friends would have opposite effects on one another. So I think anything above 1 would address at least that concern. But in practice, we would need to do something like cross-validation to assess what K would be in a more principled way. Good questions. So now we have this model for the influence dynamics, and we have this model for the outcome. And now let's ask ourselves, how do we learn about this? How do we learn what the parameters should be for this model? And the approach we'll take here is MLE. So we have in the MLE framework, we have some set of parameters, and I'll just call those parameters beta. And we're trying to maximize the probability of observing the data given all of these things that we have, given the treatment data, the outcome data in our parameters. We're trying to find the parameters which maximize the probability of observing the data that we did observe in this context. So in this case, we're going to introduce these latent variables, which will allow us to say something about this influence dynamic. We don't observe the influence dynamic, but we can postulate this interaction encoding. So this A random variable is going to tell us about which people we believe are influencing unit I. So if AI is 0, 0, 1, 1, that's going to mean that unit I is influenced by persons 3 and 4. And the model for AI is going to be the same as the one we just described in the above. And we'll make the sort of typical move which is done in the latent variable literature, where we're going to postulate the existence of this latent variable, this interaction coding, whether one person is influencing another, or which groups are influencing which other groups. We're going to assume the existence of this latent thing, and then we're going to average over that likelihood, and that is going to give us the probability of observing the outcome given the data. And we're going to maximize this. We're going to maximize this average over all the different interaction types. And this is a there are a lot of possibilities for how these influence dynamics could unfold. So we'll use a Taylor series approximation to this. I can talk more about that later on. I have some slides on that after this. But the intuition is that we're going to postulate the existence of these latent influence patterns, and we're going to do MLE using those, maximizing the probability of the data given those latent influence patterns, and then we're going to average over all the different possible ways people could be related to one another. So that's the intuition for how we're going to estimate the parameters for task 1 and also for task 2. So I've described now a framework for thinking about how influence can be inferred using covariate data, using outcome data, and then also using any measure of influence that's measured in some way, such as school friend networks and so on. Those can be incorporated into this framework as well. But now we need to think carefully about validation. So how are we going to validate this framework? And I think the first thing we can do is we can use simulation. And I'll try to make this simulation as realistic as I can make it. So we're going to have heterogeneous treatment effects in this setting. We're going to have linear covariate effects. We're going to have a sparse homophily structure. So homophily, again, means that people who are close are more likely to be connected. So you're more likely to be influenced by your neighbor than you are someone living in another state. And this dynamic will be sparse. Only one of the covariates is going to determine the influence probabilities. And we're going to use 500 observations here. Since the model that was just described is a complex one with many parameters. So we might ask, how does this operate when we just have 500 observations? And here is just writing out the structure of the model as it's been outlined here. In just the new thing for us to look at here is this term involving this log. So we have unit I, and unit I has some number of connections who are treated. So the log of the number of connections who are treated plus 1 is going to be the contribution of sort of the network to the outcome. And again, those connections are going to be based on that sparse homophily structure. And in the simulation, we're going to vary two things. The first thing we're going to vary is the number of covariates. And then the second thing that we're going to vary is the strength of the network effect. So this M here, the sign of M is going to be randomly drawn to be negative or positive. And we're going to vary the degree or the strength of M, the magnitude of M. And when we do this, we can first examine our detection rate of influence. So here we see we're on the x-axis, we're varying the interference or the influence effect magnitude. So that M term in the above is going to range from 0 to 0.1, to 0.5 to 1. And when the influence effect is 0, then our detection rate should be below some pre-specified alpha. This alpha, on the left-hand side here, we see that the false discovery rate is controlled and is less than alpha in this particular case. Alpha is set to be 0.1. So here on the left-hand side, we see the false discovery rate. And as the influence effect or as the interference effect moves away from 1, then we're examining our statistical power to pick up on influence effects when they are present. So we see as the interference effect magnitude grows, the power grows as well. In addition, we see that the number of covariates has some effect on things. As we have more covariates, the situation becomes more difficult to work with. So when we have 20 versus 10 versus 2 covariates, we generally go from worse to better. So 2 being better, 10 being worse. But we see a dynamic that generally sees good power to detect influence effects when they are present in this simulation design, when the connection model is sparse. So that's the first thing that we'll look at here. And the second thing which I'll look at is the ability to estimate the correct spillover sign. So unfortunately, we don't have time today to go through the estimation of network effects in this framework when we don't observe the true network. But to summarize that briefly, we'll use a stochastic interventions framework, which allows us to specify hypothetical ways of allocating treatments in the experiment that was responsive to the probability of connection between people in the experiment. And when we use that stochastic intervention estimation procedure, we can figure out we can compute the sign of that result and compare that to the sign that we had in the simulation, which in this case was randomly chosen to be negative or positive. And we see generally a good ability to pick up on the correct sign of the spillover effects in this case when they are non-zero. So at the left-hand side, we see if there's 0 spillover effect, the spillover effect is 0 on the left-hand side. So I don't include that here in this graph. But as soon as the spillover effect is non-zero in magnitude, then we see a good ability to pick up on the sign of that effect when it's happening. And I can go through some slides, maybe in the question and answer, going through that in more detail. But we might also ask, what is our ability to recover the centrality, the network centrality of the true network? So in this case, we don't observe the true network. The true network exists in some way, but we're trying to infer that using the machine learning paradigm that was just outlined in the above. And we can compute on the x-axis the true network centrality measure. So we can take the eigenvector, the first eigenvector of the adjacency matrix. So that's a measure of how influential people are in this context. And then we can compute the estimated centrality measure. And we see a good R squared here of 0.82. The true and the inferred network centrality have a good degree of agreement in this case. It's not perfect, but it's I think solid. So now we can ask ourselves, how does this work in real data? So in real data, the dynamics at play might be significantly more complex. And to try to see how well we're able to recover those latent influence dynamics in this setting, we're going to use the following experiment. So this was a school bullying experiment where the treatment of interest was student assignment to an anti-bullying program. And there was something unique about this experiment. So the outcome was an administrative record of the number of times students were disciplined for pure conflict. And the unique thing about this was that students were able to list up to 10 friends in the school. And these 10 friends form a kind of observed network, which we can use as an attempt to validate our approach. Are we able to reconstruct this network using only the covariate data and the outcome data in the approach described? So we're only going to use 9 covariates, including gender, including grade, participation in musical activities, GPA, the number of times tardy. And we'll also put a constraint in the likelihood that people across schools won't be interacting. That's the one constraint that we'll impose. Otherwise, we'll just use these 9 covariates to try to reconstruct the network. And secondly, we'll ask ourselves, do we arrive at the same conclusions as when we use the observed network? And the conclusion of the original paper was that there were negative significant network effects in this context. Do we pick up on that as well? And I think the answer to the first question, which revolves around inferring influence in the inferring how well do we infer that network which is observed. The results here I think are encouraging. So on this left panel, we see that on the x-axis, we're computing the network centrality of the observed graph. It's unclear in this case how good that observed network is in telling us something about true influence. So I have these question marks here by this word true. We don't observe the influence truly, we observe who lists out other people as being friends with them in the experiment. So this isn't a perfect validation, but I think it's the best that we have. That's what we have on the x-axis. We have this measure of observed network centrality using the eigenvector centrality measure. On the x-axis, we have the centrality of the inferred graph. And in these two cases, we see that in both approaches, we see that the same people are highly influential in the observed versus in the inferred network. And the same people are also non-influential. The main difference between the two is that in the case when people have a middling degree of centrality in the observed network, those people with middling centrality, we, using the inferred approach, find that they have not as much influence or not as much centrality. So that's the difference, but the similarity is that the two approaches gives us a similar sense for the people who are influential and the people who are non-influential. We can also ask whether the same sorts of covariates predict the things, whether the same sort of covariates predict influence or predict network centrality in the two cases. So in this right panel, we're going to take the x-axis here so we're going to take the network centrality measure from the observed network, and we're going to find the things that predict it, and we're going to compute that we're going to place that on the x-axis. And we're going to do the same thing for the network centrality measure using the inferred network. We're going to take that network and we're going to take that and we're going to take the covariates and predict that centrality measure using those covariates. And we see that the same sort of things predict influence in the observed versus in the true network. So things like GPA, things like absences, things like grade, both predict the centrality measure in the two cases. So that's validation in terms of reconstructing some noisy approximation of the true network. But how do things work when we attempt to replicate the results? Remember, the original study found that these network effects were significant and were negative. And in this case, we have, using the stochastic interventions framework, which I could talk more about maybe in the question and answer session, but we can compute an estimate there of this inferred network effect, which is negative, and the p-value using the approach outlined in the above is significant, arriving at similar conclusions using the inferred approach as we do when we use the observed approach. So this is validation on so this is validation on that data. And I think we can apply this to different social science experiments to see what can we learn from this. So first, I'll just apply this to 11 data sets, and I'll see what, sort of using the approach when using the testing protocol outlined in the above, when do we reject the null hypothesis of independence between those groups? And here's what we get when we run this on those 11 experiments. We're rejecting this null of independence in 4 of those cases. And one thing I like about this graph is that we have another validation in this graph. So the second experiment to the right is the survey experiment. Is a survey experiment that was done online. And that survey experiment, which was done online, likely had no influence effects present within it. So in that survey experiment, most likely what happened to one person didn't affect the outcome for someone else. So this is in a sense another validation exercise. Do we perhaps correctly reject this null of independence when most likely, do we correctly not reject this null of independence when it's most likely, that null is most likely true? We can also ask ourselves about the things like the correlation between the main effect significance and the network effect significance. So there's this correlation between the two, not perfect, but there's some signal there. Main effect significance is predicting network effect significance. But now let's turn to the question of what we can learn in an example from this, in an experiment that was done, moving back to the original experiment that we talked about at the beginning, that experiment that was done in Suffolk in the United Kingdom, in a particular part of Suffolk, Bedwastre North, which has a population of about 10,000. And in this experiment, about 3,000 were treated. In this treatment consisted of contact from Liberal Party campaigners. So this was a partisan turnout experiment. It was this contact was attempting to convince people in this study to vote for the Liberal Party in this election. And the outcome of interest is an administrative record of turnout in the May 2017 election. And the original conclusion of the study, of this, was that the effect of the intervention was positive on turnout. So the original study showed that people who received the treatment directly were more likely to turn out to vote. And moreover, the Townsley examined, using ecological inference, examined the vote totals and compared those to other elections that took place previously, and concluded that the campaign contact may have mobilized rival supporters. So Townsley concluded, using this ecological inference, that campaign contact may have mobilized people not from the Liberal Party, but from other parties to vote. And what we'll ask now is whether we can use this approach to arrive at any evidence for counterproductive network effects. That is the question that we'll ask. And the answer here, I think, is possibly. So the treatment effect, again, is positive. The intervention has a positive effect on turning out. The inferred network effect in this case, using the stochastic intervention estimation procedure, is negative, and p-value is significant. And we can learn more about how to interpret this by looking at the central people in this setting. So the central people in the setting, so the central people in the inferred network are Liberal Party members as well as likely voters. So most likely, using this framework, we can conjecture that the campaign may have had a counterproductive effect. Not only may have it mobilized people of other parties at the individual level, but it may have demobilized the Liberal Party. So the conclusion here is that the random targeting of households, that the Liberal Party campaign overall may have been quite counterproductive from the perspective of the party organizers. So this is some of the sorts of things that we can learn from this approach, and I think we can use the results from this analysis in a sequential in the sequential design of experiments in order to target different sorts of people in order to maximize turnout or in order to produce some effect. So this can not only tell us something about influence structures, but it also potentially can be used in the sequential design of experiments. So just in conclusion, influence, I think, is essential to politics, and this is essential not only at the level of voters, but also at the level of political organizations and states. And this is these influence dynamics have an unbelievable degree of complexity associated with them. And I think this calls for a new machine learning paradigm, which uses all the information at our disposal in order to infer something about likely influence structures present within the study of interest. And finally, I think this sort of framework can also help us start to think about individual level questions about influence, which I think are relevant to a whole host of different areas, from the Supreme Court to the study of experiments, where we might want to know about the kinds of people who are influenced by which other kinds of people in this sort of study. So this is what I have to present today. I'm happy to take any questions, any comments, and to have a great discussion. So thank you for listening to the presentation.
Connor, I have a question. So I'm just confused, I think, by the definition of influence.
Mm-hmm.
And this is not my field, obviously, so maybe I'm just missing something, but so the way I read just the definition of influence that you gave at the beginning was this like an independence assumption between what I thought was the treatment assignment and the potential outcomes. Yeah. And W here means the treatment, right? Is that?
Yes.
Yeah. So I guess I'm a little confused by this, because my understanding about the way I would define influence would be whether or not the potential outcomes are a function of little wj, not for unit I, not whether or not these things are independent. Because unless I'm misunderstanding something, this no influence would hold in a randomized experiment because of randomly assigned W.
Yeah. So that's a good question. The way that I'm thinking about it is that Wi is so Wj is a random variable, and Wi is a function of that random variable in this case. So the way I'm thinking about it, yeah, so you're right. The assignment to what happens to J is in an experiment independent from all of the potential outcomes. But what happens, the random, we can think about Yi as a function, and that function is, that function takes in as its input that random variable about what happens to J. So
just to be clear then, so this is equivalent. So I guess, yeah, I missed it. Big W bold here is the observed value, the observed treatment assignment for this particular experiment. So this is basically saying if Wj is independent of Y, observed Y.
Yes, essentially, the observed Y.
Okay. So but it could still be the case. So yeah, I guess it would be nice. I mean, one thing that would be nice, it seems like previous definitions of influence or interference, or however you want to call it, have defined things in terms of, does the potential outcome function depend on, Wj, little w, the spot in this function that is W, little wj. And I guess it would be nice to be able to connect those two definitions a little bit. So, because sometimes in the talk you kind of veer between influence and interference. And I think it'd be good to kind of know how those two things relate. Like, does this, for instance, like one question would be, does this imply that there's no interference at, like this is an average level statement. So this doesn't necessarily imply that there's no influence at the individual level, right? This is like an average level statement.
This here would be, so if this independence relationship holds, then the function that determines I's action doesn't take in as input what happened to unit J. So you could rewrite this using that notation where like you have you could rewrite this sort of definition using instead of W here, instead of big W here, a capitalized W, we could rewrite this definition using little w's, and for at least one treatment combination, changing what happens to J changes unit I's action. so we could rewrite that in that way.
And then, so I guess like a follow-up question is, does that mean, so when you're doing this randomization test, and so again, I think like other folks, I didn't quite follow the logic of it exactly, but so are you, is this, so because like the thing you just said is a sharp null. And again, maybe I'm missing something, but this doesn't seem to be the thing that the null hypothesis that you just stated on the other slide, that it does not seem to be a sharp null.
Mm-hmm.
And so are you using a sharp null to fill out the kind of potential outcomes and then do randomization inference on that? Is that how this is proceeding, or no? And so, and maybe this relates to Kosuke's question about conditioning on the y, like the observed y's.
Mm-hmm.
And I'm just, I guess, yeah, I'm a little lost in that, in the weeds on this,
Mm-hmm.
this question.
Yeah, that's a good question. So the relationship, is this a sharp null? So I think, so as for the, let's go to the test here. Maybe that will help clarify things. So here, in the sharp null approach, we don't resample, we wouldn't resample the sort of this part of the treatment vector from its known distribution in that way. We would, well, we could permute the values associated with people in that testing set, sort of scramble them, permute them, and see whether things change. So the framework here won't be doing that. Instead, we're going to be drawing this quantity again from its known distribution, like we were rerunning the experiment again. So here we can think about, let's imagine that we have two schools. We use the first school to learn sort of the function relating all the treatment dynamics, all of the covariate dynamics with influence and with the outcome. So we could use that first school to learn about how this function operates. And then we could apply that function to people in the second school, and we could resample this part of the treatment vector from its known distribution and take the way that we've learned about things from that first school and apply it to that second school. So if we have one person in that second school, we can apply our knowledge from that second school to learn about how things in the first school operate, and then the sort of the simulated treatment vector there isn't going to be a permuted version of it. Instead, it's going to be redrawn from its known distribution, which allows us to analyze the distribution of the test statistic under the case when we fix the treatment, and the case when we use the simulated version of it. But it's a good question. I'll clarify in the future the relationship between the sharp null here. I think thinking about things in the sharp null framework gets difficult because we have to think about which subgroup the sharp null holds in, and it makes the whole analysis complicated in a way that I think this approach sort of eases up from to some extent. But it's a good question.
Connor, I just want to say, I think there's a really important idea here, which is being data adaptive in how you use structures of interference rather than just assuming them to be known ex ante. And that implies, extensions to even using this approach, even when you have the network, because you can do better than just using the naive measure by using outcome data. So I think there's something really important there. And I think roughly the way in which you're estimating these things seems reasonable. The only thing I wanted to suggest was, I think, reflecting Professor Amai's remarks, is just to plug this into the AFI, Eccles, and Invents framework, rather than trying to reinvent the wheel to test them. These things have basically been worked out, and you can think of this as basically doing plug-in estimation of the test statistic in these other settings. And so that strikes me as a way to just do better than one would do naively. Trying to reinvent the wheel with these definitions is going to cause you problems. The main one is that your definition of influence is not structural. The easiest way that you can see that is to consider pair randomization, where flipping one unit's treatment would causally affect someone else's outcome, but it's not in any way attributable to a structural parameter. for that reason, you know, this is testing for existence is the right thing to be doing here, I think, because you don't need to get the oracle to get a valid answer. So I think this is all like basically morally correct. But there's a lot of I think there's work in fitting this into existing statistical paradigms that will make it much easier for everyone to read and to make it technically correct. Thank you.
Thank you. I think that's a great comment. I think I can show a graph illustrating sort of a statistical power using this framework when we do not use the kind of outcome-driven, data-driven approach towards arriving at that test statistic. So if we don't use any of the outcome data to calibrate things in that machine learning paradigm, we can do the same sort of analysis that we did in the above, and we see that our statistical power is quite limited in that sense. So I think using a data-driven approach towards the formulation of the test statistic, it does seem to make a big difference in practice. Are there other comments or questions?
Hi, Connor.
Hello.
So to the extent that this is a practice job talk, I have a couple of suggestions for like just a presentation. So I think in your empirical illustrations, you showed us your estimates of like the network effects in addition to the testing of null hypothesis. So in the first couple of slides, you might spend some space laying out your estimates and also the assumptions for your testing framework. Because otherwise people might be lost because I don't see a clear definition of the network effects and also the assumptions for connecting the potential outcomes and testing methods.
No, I think that's right. I think the network effects here are being calculated in the stochastic interventions sort of framework. So we can
you might want to move these definitions to the beginning.
Okay, that sounds good. So just to give maybe some brief background for this, the hypothetical question that we ask here in computing those sort of effects is what would the average outcome be if the experimenter had treated unit i's likely connections with higher probabilities? So we can think about that sort of thing. So this is an example here. So in most experiments, if there's just binomial randomization, then the probability that I influences J doesn't affect the probability that J is equal to 1 or not. There's no relationship between influence probabilities and the randomization probability. When there is in the hypothetical assignment strategy that we're going to consider, we can think about upweighting the probability of treatment assignment for likely connections and downweighting the probability of assignment for unlikely connections. So we can use that sort of hypothetical assignment strategy, and then we can compute sort of a stochastic interventions estimand and use an inverse probability weighting estimator to try to get at that quantity of interest, which somehow intuitively should tell us what would happen if we were more likely to treat those who are more likely to be connected or not. And that's how we're doing it there. So I can add that to the above to make that more transparent.
Connor, I wonder that might be too much. So just sort of reflecting what people have been saying, there's a lot of like complicated stuff going on. There's, I think, the part where you sort of revisit this randomization test framework, conditional randomization test framework, and then there's the part that has a lot of machine learning jargons that's neural nets and all that. And if you add this, I think it's just going to overwhelm the audience. So I wonder if you just like make it, start with much simpler. You're trying to get the first understanding the testing framework, which I think like you can revisit what the framework that's being used in the literature, like Peter and others have developed, where basically they've done this conditional randomization test for the detecting the spillover effects. And then you say, okay, but we know a little bit more about networks that exist, potential ways that one person influences another. We hopefully have the data. How do we use this, right, to increase the statistical power? But we don't want to make assumptions about how they exactly influence each other, but we know a little bit about, potential ways that people influence each other. And then try to sort of bring in some of this network modeling and then show how that fits in this, standard conditional randomization testing framework, and then show how effective that could be in the real applications. That's a lot easier. And then you don't have to worry too much about neural nets and all that stuff, right? It's more conceptual. But that part is really implementation, I assume, right? Is that?
Yes, that part, in a way, that part it's not essential. The essential part is elsewhere. That's just one realization for a general idea.
Yeah, so I think that would make it, easier. Because there's a tension between, on one hand, people assume some network model, assume the structural, inference patterns, and then do some parametric analysis, which may not be credible if the model is wrong. And on the other hand, there's more, assumption-free approach, but hasn't really exploited the use, the availability of the network information. And you're sort of combining the two.
Yes, no, I think that's right. I can beef up the context, down-emphasize the machine learning details, and then try to work that in a more unified way.
Yeah, I mean, another thing is I think a lot of confusion that mine included comes from different notation, different, sort of unstandard presentation. So it's like notation is like our language. So if you change that often confuses people.
Mm-hmm.
So you might want to look at the existing papers and then follow the way they formulate things, or at least connect, like Matt was saying. That would make it much easier to follow. Because right now it's really hard to. I mean, if you're confusing us, you're going to confuse a lot of other people.
Mm-hmm. Okay, that sounds good. Are there any other comments? Any other questions?
Connor, just a quick thing. I agree with Gosuke that simplifying things, figuring out where you need the notation and where you can just describe things in higher level detail is important. And then I think this is just I feel like I looked down for a second. I looked up and there was an A variable, and I was like, I don't know what this variable. I don't know what this is. I have no idea what this is, and it didn't seem to connect back to the things that you were doing at the beginning. And so you have two sets of notation, and so dropping an entire set would probably be useful from the point of view of just keeping the audience informed. And in general, what's nice about machine learning and this kind of this stuff is that it is plug and play. It's like a black box that things go in, and you can describe it like that and say it's very complicated and you did a lot of work to make it work, but the audience doesn't need to know the details so much, I think. The only other thing is I think you said, this is super minor, but I think you said Liberal Party a lot, and I think you meant Lib Dems. And at least that's what the original experiment said. And that's if you can give this talk at someone there's British politics in the audience, I think it's just going to drive them up a wall. So, I think just, getting little details like that, I know it's incredibly minor, but that's the kind of thing that just pisses off some random person in the room. And the last thing you want to do is piss off someone in the room in a way that for such a silly thing. So that's just something you'll figure out. But that was just one thing that I noticed. So.
Okay, no, that's a good point. Point well taken. Thank you.
Any other questions or comments to Connor? If not, thank you so much, Connor.
Thank you very much. Thank you, everyone, for coming.
Thanks, Connor.
Yeah, good job, Connor.